Very good morning to all of you, and thank you very much for having me here. I'm going to talk about additive manufacturing and surface engineering, and my name is Ashish Ganvir. I started at University of Turku in April 2021 as an assistant professor in the newly established Department of Mechanical and Materials Engineering. Before that, I was working in industry in Sweden, in GKN Aerospace, as a process engineer for additive manufacturing for about 2.5 years. When it comes to my academic qualification, I have a Bachelor of Technology degree from IIT Kanpur in India in Material Science and Metallurgical Engineering, and Masters in Mechanical Engineering from University West in Sweden, and also PhD from the same university in Production Technology with the specialization in plasma spray. I have also done 2 postdocs. The first one was focusing on biomedical coatings and graphene reinforced ceramic matrix composites, and the second postdoc was focusing on tribology. When it comes to my research profile and domain, I would like to keep it in divided into these 2 fields, additive manufacturing and surface engineering. And typically I try to use my experience and knowledge in material science and process engineering to tackle the challenges in these 2 fields, and this is something that I'm going to discuss in the next 20 to 30 minutes with you. So let me start with the additive manufacturing first. Before that, let's try to get familiar with the traditional manufacturing routes that we experienced so far. So if we divide the traditional manufacturing routes, then we can divide it into 4 classes or 4 categories. The first one is the subtractive manufacturing, for example, machining, drilling, milling. Then we have a separating type of manufacturing like cutting, sawing, etc. Then we have joining sort of manufacturing like welding, brazing, cladding, thermal spray. And finally, we have forming type of manufacturing like casting, forging, etc. And now with this new way of manufacturing, which is additive manufacturing, coming into the picture, we will have an addition to these 4 categories. So what is additive manufacturing? When you try to look at AM on internet, you will find several definitions, but the one that I prefer to use is the one given by ASTM F42 standard, and it defines AM as a process which uses digital 3-dimensional design data to build up a component in layer by layer fashion by depositing various types of materials like metals, ceramics, plastics, and their composites. When it comes to my focus, so far it has been on metals and their composites in AM, but I would like to take this beyond that and use it for ceramics, plastics, and their composites also. The 3 basic ingredients that are essential for any additive manufacturing technology are first the digital data. This digital data is can be in the form of the 3-dimensional CAD model or a robot path. The second one is feedstock. This is the raw material that we need, and this can be in the form of powder, it can be wire, it can be sheet, or it can also be liquid. And the last ingredient is heat source. So in this case, we can have a laser beam, we can have an electron beam, or a plasma, for instance. Now together these 3 ingredients can create 3-dimensional components in a layer by layer fashion, just like what you are seeing in this schematic here. So this is additive manufacturing. So why should we board this additive manufacturing express? What's the reason? So there are many advantages that additive manufacturing can offer as compared to the traditional manufacturing route, but the 3 most significant that I believe should motivate most of us to buy the ticket are these one: the increased design freedom, that you can almost imagine any design and try, you can realize that in reality using AM, which is otherwise rather difficult if we use traditional manufacturing routes. The second one is the reduced material wastage. AM offers these advantages over at least some of the traditional manufacturing routes like subtractive and separating manufacturing. And the final one is the shorter lead time. So basically, from the idea that comes to your mind that I want to design this particular component to finally making it reality and bringing into the market, the overall duration is significantly reduced compared to some of the traditional manufacturing routes, and this is also one of the advantages that AM offers. So there are many more, but I'm pretty sure that at least these three are enough to motivate you to board this train. Another motivation that I would like to give you by explaining this simple case study of a bottle opener. I'm pretty sure most of us have used this bottle opener in our life. If not used, then at least have seen the bottle opener, right? So how do we manufacture this bottle opener traditionally? So we have a sheet, a material of certain material of a certain thickness, and then we machine out or mill out the certain shape that we would like to have it in the bottle opener. And this is what you see on the slide on the left side here, how simple shaped bottle openers are manufactured. Now with the use of AM, as you can see on the right side of the slide, you have a possibility to create rather complex design for the same functionality, and this too in rather short lead time with less toolings and significant reduced material waste. All of this will lead towards the sustainable manufacturing, something that we are all trying to aim so that we can solve this climate change. AM is not only restricted to a certain length scale, it can create components at almost all the length scales that we can imagine now. So we are talking about creating components at micrometer level to millimeters to centimeters to even few meters. And my current focus so far has been around the centimeter length scale, but I wish to extend this beyond that towards large scale additive manufacturing and also towards the small scale additive manufacturing during my professorship. Despite of several advantages that AM offers, of course there are limitations. And this is also for people like us, for researchers, this is an opportunity because that's where our role comes into the picture. We want to solve this. So what are those limitations? So the first one is limited materials for AM. So I think we still have a lot to do on creating knowledge on how many materials we can process using AM. Even if we can process certain materials, the components that are manufactured observe presence of defects, anomalies, which can lead to degradation of material properties. Dimensional accuracy and the presence of excessive residual stresses is also one of the challenge, and this area needs to be also better understood and solved accordingly. Most of the components that we can manufacture using AM, especially for metal, the surface quality of the metal components are rather poor, and that needs to be also understood. How can we engineer the surfaces? How can we modify them? And the need of excessive post processing also needs to be at least minimized, if not totally removed. Some of the materials are kind of considered as matured for some of the AM processes until now, but even in these particular cases there are challenges like how robust is the process for that material, what are the quality control issues that we know about it. So these are the challenges that also needs to be solved. And the last one is a limited number of standards available for both the AM process and also the materials that we use in AM. So all of these challenges, which for me is potential to do research, is something that I will tackle during my professorship. AM is not only used to create these three-dimensional bulk components. It has a lot to offer in the repair and remanufacturing sector. So if the components are damaged, what we traditionally try to do is we replace this with the new components. Now with the use of AM, we can actually just repair or remanufacture that part, sometimes even on site. So that is what I meant by using AM for repair and remanufacturing, and it has a lot to offer for several sectors like aerospace, automotive, marine, power plants, biomedical, defense. These are just a few that I can list down here. And this repair and remanufacturing is a real sustainable solution to modern manufacturing, because it can not only save the cost, but significant material waste is also reduced. So what are the different techniques, AM techniques that can do this repair and remanufacturing? So some of the potential AM techniques that are already in use or have potential to be used are direct energy deposition using powder and wire, cold spray, cladding, and also powder bed. Now my focus so far has been particularly on DED using powder, but the ambition is to also explore these other technologies moving forward for repair and remanufacturing application. So this was about the additive manufacturing area. Now I wish to talk about also the other aspect of my research, and that is the surface engineering and coatings. I am pretty sure that most of us have experienced the benefits of surface engineering in our life, but we may not have really thought about what it is. So let me try to define the surface engineering for you. So according to this ASTM handbook, surface engineering is defined as a method to treat the surface and the near surface region of a component, so that we can allow that surface to perform functions that are totally distinct than the functions demanded from the bulk component. So basically we are imparting or giving an additional functionality to the component by modifying the surfaces. So that is the surface engineering. Why we need to engineer the surfaces? Because most of the time the components that we prepare and the material properties of those bulk components are typically optimized for properties like strength, stiffness, toughness, formability, and cost. But when we use these components in reality, they still remain vulnerable to surface degradation issues like wear, corrosion, thermal fatigue, thermal shock, and there are many. And these surface degradation issues needs to be better understood and solved accordingly, so that the lifespan of the components can be extended. So this is also one of the area that I have been exploring so far before joining University of Turku, and I will carry forward that. So how to engineer the surface? So there are two ways that you can do that. One is by adding a coating on a component, and other route is that we do not add a coating, we just modify the surface. So let's try to understand the second scenario first, where we modify the surface by means of mechanical or thermal means. For instance, grid blasting, shot pinning, grinding, polishing, heat treatment are some of these examples. Another category is when we add coating, and in this we have two classes. The first one is diffusion sort of coatings. So in this case we take the component and place it in an environment where certain elements can diffuse in the material and form this diffusion coating. Some of the examples are carburized, nitrided, and aluminized coatings. And another class to this is overlay kind of coating, where we physically deposit the same material or a different material coating on top of the component. And this can be achieved by certain technologies like thermal spray and cladding. So there exist many surface engineering techniques that you can use to modify the surfaces. But the one that comes under my horizon are the thermal sprayed coatings and cladded coatings. And so far my main focus has been on how to use plasma spray for solving some surface engineering challenges, and this is something that I will carry forward at least in the early phase of my professorship here at University of Turku, and also focus in future on several other technologies that you can see here highlighted in the blue color. So now let me try to give you some idea about especially the plasma spray and what I have done, and what are my ambitions around that technology, and how I can help the various industries using plasma spray. So plasma spray is one of the thermal spray process where we use feedstock or a raw material in the form of most typically powders, but we can use wire, we can use also liquid, and we inject these raw materials or feedstock into the plasma, where the material is melted and accelerated with certain speed towards the component, where this molten material splashes the component and forms something like pancakes. We call them splats, and these pancakes are deposited on top of each other, on beside each other, and this layer by layer splat deposition creates a coating. Now typical powder size that is used to do this is about 10 to 100 micrometer. This is rather coarse powder size we are talking about. Now imagine that we want to create coatings that have microstructures with features like down to few nanometers, and if you want to do that using the raw material of the order of like 10 to 100 micrometer is not going to help, and the idea is then we can reduce the powder size, the raw material size to few nanometers. The issue with that is it's not easy to inject or feed that sort of size into the plasma because of the flowability issues that these fine powders have. So the solution to that is we can mix this powder in a liquid media like water or any non-aqueous media to create a suspension, or we can use directly a solution precursor that can in situ create or form this material in the plasma. So that is called liquid feedstock plasma spray, and this has been one of the workhorse for me during my research, and something that I will also carry forward here. The biggest advantage, as I already described, is the ability to feed these fine nano scale powder particles in the plasma, which gives us an advantage to have features down to few nanometers, like the pores that you see here and the grains that you see are extremely fine. And in addition to that, this technology also offers a lot of possibilities to create various coating architectures, like we can have multi-layered coatings, we can have composite coatings, we can grade the different materials to create coatings. We can create coatings with more than 50% porosity for some applications like insulation. We can create coatings which are extremely dense, extremely thin, and so on. So all these different architecture possibility that this technology offers gives us also an opportunity to look at many applications, right? So some of the potential applications that I'm listing out here are some of them I have already explored. For instance, before joining to University of Turku, like using this for producing biomedical coatings for medical implants, producing coating for thermal barrier application on the gas turbine engines, coatings for tribological applications. So these were the areas that I already explored, and moving forward I wish to use this technology especially for energy application, for hydrogen production, for batteries, for fuel cells, and so on. So there are many more that we can actually think about using this technology. So to summarize, I would say both these fields that I wish to work upon, additive manufacturing as well as surface engineering and coatings, has a lot to offer to various industries, biomedical, green energy, automotive, marine, power, aerospace, space, defense, many, many more. And I'm really hoping that I will be able to do, I will be able to contribute by solving some of the challenges that these industry and society are facing using both additive manufacturing and surface engineering during my professorship. So with this, I would like to thank you very much, and I wish you a very safe, healthy and happy stay.